So today we are going to essentially apply all what we have done together in lecture on the blackboard. So we started already yesterday to see how in essentially a quantum dot with a single contact or with a superconducting contact, we could in fact already see some of the very I think interesting things which we could do by coupling quantum dots with microwave cavities. And today I will show you, I will discuss three topics. First of all, the topic which is in fact the reason why, I mean, all the people in this area started to work on, which is whether it's possible to engineer the strong coupling between quantum dot circuits and microwave resonators. The second, I will show you that we can go even further on the condensed matter topics with the use of cavity, the cavity as a very sensitive probe of Kondo correlations. And finally, I will show you a theory proposal which we did with Audrey Cotet and Benoît Dussault and Matthew Dartiaille to probe, I mean, a theory proposal it shows you how the cavity photons can be used as a very sensitive probe of Majorana excitations. Okay, so again, so I start. So this is the group. I mean, some time ago with Jérémy Viennot, Mathieu Desjardins, who did the Kondo work, Laure Bruat, who did the strong coupling work, and Matthew Dartiaille contributed to all these topics and also did the theory proposal, and there is Audrey Cotet and myself. And there are newcomers in the team, Tino Kubens, now Matthew Delbecq is coming back, and Lauriane Contamin. And on the theory side, we have benefited for the numeric polynormalization group from a very nice collaboration with Mansu Choi and Mincho Lee. And there is, of course, Benoît Dussault. So let's start now from the beginning. It's very much like what Jason has talked to you about. So Cavity-QED deals with the interaction between light and matter at the most elementary level, so down to a single atom and a single photon. This is an example which we particularly like in Paris. And so this is the Rydberg atom in the microwave mirror cavity, superconducting cavity. And this is essentially this is a Cooper pair box in a coplanar waveguide resonator. And in fact, these two systems, although they look very different, they can to a great extent be described by this simple Hamiltonian, which is the James-Cummings Hamiltonian, which you have a spin 1/2 here, you have the cavity photons, you have the coupling term. And one particularly interesting regime happens when you're in a strong coupling regime, meaning that this coupling strength here is larger than the dissipation of both the photon and the atom. So this is so I have omitted the bath here, but there are some baths and there is dissipation of photon and atom. And so the question is whether, I mean, we will be able to investigate that kind of physics, not with superconducting circuits or atoms, but with quantum dot circuits. So as you remember from the two previous lectures, so we have coplanar waveguide cavities, and so this lie in microwave range with quality factors of about 15,000. And the measurements are carried out about 20 to 250 millikelvin. And as we saw in the lectures, there are two limiting cases which are interesting. So there is the case of a closed quantum system, so which for us will be a double quantum dot. So where you have, for example, a charge sitting on the left and being able to hop on the right. And you have the open quantum system limit, where you have a single dot which allows you to essentially revisit impurity physics in condensed matter. Okay, and as we saw, I mean, deriving this coupling form, this Hamiltonian, which describes the coupling with very general arguments between these kind of systems and cavity photons, you can have two kinds of transitions. So the photons can bring the charge, essentially the charge from the left to the right. So this is interesting for quantum information. If you want to talk to, you want the photons to talk to internal transitions. And this is, the photons can bring essentially this charge from the dot here to the reservoirs. And this gives rise to very large electrical dipoles, as we saw, because it's just a ratio of the impedances, the square root of the impedance line and the quantum resistance times the frequency of the resonator, essentially up to a lever arm from the capacitive coupling. And this leads to a very, very large dipoles due to the mesoscopic scaling. Okay, and so again, so the idea why, I mean, people started to work with quantum dots in cavities is related to the question of whether it is possible to transfer the ideas of cavity quantum electrodynamics or circuit quantum electrodynamics, which have taught us how to probe, manipulate macroscopic or microscopic quantum states to hybrid mesoscopic circuits, and in particular to quantum dot circuits. And so there are two questions, in fact, which, as I told you, we will try to answer today. Is first, maybe one very important question, which is it possible to achieve the strong coupling with quantum dot circuits? And the second question is that whether it's possible, I mean, to use this kind of architecture to address condensed matter questions, because you see that, in fact, you can just imagine to attach these quantum dots to normal leads, but also to superconducting or ferromagnetic leads. And you can also put several dots, so you can imagine to some kind of engineer a condensed matter situation with that kind of systems. Okay, and as we saw in the lecture, there are two limiting cases which are interesting. So the first limiting case is the case of a closed quantum system. So here you see that you remember that we derived this expression for the cavity transmission with the coupling strength here. This is the susceptibility of a generic double quantum dot with a resonance here at a definite frequency. And essentially, each time the cavity is resonant with this frequency, you have very large signals in the cavity, which are related to the real part or the imaginary part of this charge susceptibility, and which essentially mean that when the charge or the spin state energy is crossing the energy of the resonator, when, for example, you change a control parameter on one of these systems, you have very large signals, and which means that the cavity provides essentially a cut of the double quantum dot spectrum at the cavity frequency, essentially. And then there is the other limiting case, which we, in fact, started to look at more carefully yesterday. So again, this is the same form of the cavity transmission. And in the adiabatic regime, meaning that essentially you have a generic conductor, so mesoscopic conductor in the cavity. Essentially, the cavity photons are shaking adiabatically back and forth the chemical potential, and this ends up by a direct measurement of the compressibility of the electron gas. And this is a very interesting quantity to look at, especially when you have strong correlations between the electrons. And okay, you can derive a more complex formula, which we have tested in this paper. But what is really important is that, so we will apply this formula at the end for Majorana oriented devices. Okay, and so so now we will first, before going into whether it is possible to achieve the strong coupling regime between so quantum dot circuit. So for us, it's going to be a double quantum dot, like this one, for example. So we have to it's interesting to see whether it is possible with the simple equations which we wrote down on the blackboard yesterday to understand the data which is typically observed in that kind of setups. So this is so for any kind of double quantum dot, things which you observe typically are essentially this. So, so this is I take one of the early papers by the group of Zurich, and in fact, similar. I mean, so in fact, Jason showed similar view graphs with his systems in the Resonator nanowires. But essentially, the idea is that there are two situations which can occur. So you remember here. This is the excitation which we wrote down. So this is the square root of epsilon delta squared plus 4t squared, which we found this is just the energy, the transition energy of the double quantum dot. And there are two possibilities. First, as a function of the control parameter, which is the detuning. So we called it epsilon delta yesterday. Now it's called delta epsilon, so I'm sorry it's not consistent with the notations. Essentially, what happens is that in this situation, the cavity frequency is never resonant with the double quantum dot transition frequency. And so which means that, so this 2t here is larger than the cavity frequency. In this case, so typically you have that kind of plot for the shift of the microwave, of the frequency of the microwave cavity, and the shift of its damping. And you see the red line here is essentially the formula which we established together yesterday. So you see that there is a pretty good understanding, I mean, in these kind of systems. And here this allows, okay, and here this is a regime where you cannot very sensitively determine the dephasing time of the transverse relaxation time of the double quantum dot, but it turns out that it's fairly large. And which is reflected in the fact that the shift in the frequency here and in the damping of the cavity is not so large, although there is a very large coupling. So one very interesting thing happens when now you have 2 points here which are resonant between the cavity and the double quantum dot. This is again in the same paper. So you see that now you have a sign change in the phase. So this is what we saw yesterday. So there is the real part of chi, I mean of the susceptibility, is not necessarily always a constant sign, and therefore you can have, depending on the relative frequencies between the double quantum dot and the cavity, it can lead to a sign change in the phase, and you see again this red curve here, which allows to fit quantitatively the data. Here the agreement is not so good for the dissipative, but nevertheless qualitatively it works. So this is again just, I mean, what we wrote down yesterday on the blackboard. As you see that what we wrote down is pretty predictive. It kind of, I mean, allows us to, allow one to understand what is going on in these kind of systems. What you see also is that the decoherence rate is fairly large here. So again, there is not such a big shift. You see it's 0.5 megahertz, the shift of the cavity frequency. And it's related to the fact that you have very large disphasing. So as I told you before, the strong coupling occurs when this guy is bigger than the cavity line width. So this is okay because the line width in this experiment was about, I think it was several megahertz, 3 megahertz as far as I remember. But it's definitely not okay here because you see the decoherence rate is way too large. So in fact, you can test further and try to find, situations where it's slightly more coherent. This is one of our devices. So this is the work by Jeremy Viennot. And so you see that you start to see in this situation, you see it start to be sharper here. But obviously, what you would like this to be is really to go up, and down for large amplitudes, which would mean that you would have some very strong changes in the cavity line width or transmission spectrum when you are in these two situations. So again, here the coupling here was quite small, and although we could get down for the decoherence rate, it was still way too large. Okay, And this is reflected in the cooperativity of our system here, which is not so great. So in fact, here it was 0.03, which tells you that here you are far from the strong coupling regime. Okay. So now, now the question. So now essentially, at that time, people would tell us, no, but I mean, this is normal. The charge is completely lousy. I mean, for you cannot have any long-lived quantum states with the charge, and you will never get into the strong coupling limit. But it turns out that last year, I mean, so there were three groups which achieved with the charge the strong coupling limit, and therefore I will show you that so in our devices that one can achieve indeed the strong coupling limit with quantum dot circuits. Okay, but in order to achieve the strong coupling, one has first to make the samples, and this is how we make the samples. So here is a typical sketch of how we make the samples. So we have a coupler waveguide resonator. So here you see that you have the input here and the output, and you have some DC control knobs here. So and this is made in niobium for us. And essentially, in order to keep a good microwave properties of this coupler waveguide resonator, what we do is that we grow our nanotubes on a separate quartz substrate, so there are quartz pillars, and essentially we flip over the quartz pillars and we align with the mask aligner these quartz to the pockets here where we have antinodes of the electric field, and we stamp essentially the nanotube inside these pockets. And like this, we can have quality factors of about over 10,000 at least, from 10 to 30,000, and with a very low density of carbon nanotubes, which allows to pick up individual nanotubes for making our devices. So here is how it looks like. So this is a quartz with catalyst on it before the growth, and this is after the stamping on a silicon substrate. So you see a nanotube here, which is going out from the stamp on the silicon substrate. And on this nanotube, for example, we will essentially try to make a device. Okay, and the measurement setup is like that. So again, this is our microwave cavity. So the mirrors, as I explained, are interruptions in the central conductor. And you have also a DC gate, so DC control knobs, so low frequency control knobs. And what is very important is that we can simultaneously measure the transmission of this microwave cavity, so with a cryogenic amplifier, and the DC current which flows through the device. So this is going to be very important for the second part of the talk. And so here is the sample in which the sample scheme in which we observe the strong coupling. So here it's kind of a hybrid double quantum dot in the sense that we have a superconducting electrode which is thermocoupled to the nanotube. So it's not a conventional quantum dot. And you have two outer normal electrodes, and you have essentially two side gates. So these are the control knobs, which allow us to control the left and the right dot. And what is important is that we have this fork here. So this fork allows us to go to, this fork goes directly to the central conductor of the resonator. It's important in order to shake simultaneously the two energy levels of the double dot. So the coupling scheme now is slightly different to what I explained to you yesterday. Now we couple for a reason which is related to the superconductor. We couple to the not to the difference of the energies, but to the average. But apart from that, it works the same as before, and we measure simultaneously the currents and the resonator transmission. So for this particular resonator, the quality factor was about 10,000, and the cavity resonance frequency was at 6.64 and so gigahertz. And the measurements were carried out at 20 millikelvin. And essentially, when we tune now in this region, so we try to bring, in resonance the quantum dot and the cavity resonance. You have essential. Yeah. So the role of the superconductor is to shape the spectrum of the double quantum dot and make the tunneling between the left and the right dot sensitive to the average of the energies between the left and the right dot, because you have additional processes where you essentially there is one electron which goes virtually into the superconductor and goes back and goes to the other dot. So this kind of elastic co-tunneling or Cooper pair assisted tunneling makes the T now depend on the average of the energies. And therefore, this gives you a new coupling mechanism. Yeah. So it couples it's an extra coupling mechanism between the two dots. Yeah. So there is the ordinary barrier, but there's also a path which goes from the superconductor, and this makes the transmission this makes an effective barrier, which has the ordinary tunneling plus the Cooper pair assisted tunneling, and this gives a new coupling mechanism, because now the microwaves, they can couple to the average. They couple very strongly to the average, actually more strongly than to the difference, and which means that in the Bloch-sphere language, you can essentially shake not only the difference, but also the T. So you have another coupling mechanism. It's important here, yeah, because you see these big fork shunts, the left and the right dot, and this is important for reducing the decoherence, as you will see. So let's. So and then okay, so this is what we observe when we tune the two dots. The dots. The device with the cavity, and so this here is measured at essentially a power which corresponds to roughly 1 photon in the cavity. And this is a vacuum rabbit splitting, which is about 3 times the line width. So you remember yesterday what we saw is that in fact when you write down the susceptibility of the double quantum dot, so in fact if I go back to the here, in fact there was an extra term here. It was just not like G squared times chi, where chi is 1 over this. But there was a difference in the populations. There was the sigma z. This was n minus, like the anti-bonding minus the bonding here occupations, which we wrote down yesterday. And this is typical of when you write down the equation of the coupled equation of motions of a spin 1/2 with a cavity. You have the expectation value of sigma z here, meaning that now if you shine a lot of photons in order to saturate the transition, and you will make sigma z 0, then you should lose the strong coupling and recover the bare cavity resonance. And this is in fact what we checked here. But that tells you that you don't have only 2 coupled oscillators, but you have something which is a very nonlinear interaction. You have a 2-level ideally, or a few-level system in our case, coupled to the resonator. And this is what this view graph. This is what this is shown on this view graph, and this is what is shown also here. So now this is exactly the same tuning parameters, but now instead of having about 1 photon in the cavity, I have 400 photons in the cavity. And you see that it's completely different. Now I have a single peak here, and this single peak is just is essentially the bare cavity resonance line, the resonance transmission spectrum, and in fact you see the continuous evolution of this on this view graph, which is the cavity transmission spectrum as a function of the photon number. And so we can understand quantitatively with a slightly more complex modeling of this of this of our system involving the value degree of freedom because we have nanotube. But what we can say here is that we have indeed observed a strong coupling between a quantum dot circuit and microwave cavity. Even though here we have primarily a charge degree of freedom, so which is a priori, which was a priori not very coherent, but this is so this is definitely the hallmark of the strong coupling regime. So how come? I mean, there are like three, groups which could find the strong coupling regime, and in fact there are three different reasons, and they are all related in fighting the dephasing to charge noise essentially. So essentially, in all these charge qubits, essentially, as a function of time, you have so this is a blast sphere. The transition frequency is in fact sensitive to the local charge noise in these devices, and therefore fluctuates in time. Which means that if you have a free induction decay, for example, pre-evolution of the system, in fact, the phase will be random after some point, and this is what has prevented people to observe the strong coupling so far, because this was too large. So there are three. There are at least three options, but there are here the three options. So there are the two classes. First, you say, okay, I have to live with that I have to increase the coupling. So this is what they did in Zurich. So you remember what we showed is that the coupling strength was the ratio, the square root of the ratio between the line impedance and the quantum resistance. So if you increase the line impedance by, for example, having a squid array, this is what they did in Zurich. Then you will get to a much larger coupling strength, and this is what they did in Zurich. So they got a coupling strength over the decoherence rate of about 1.2, which is exactly the regime to have the strong coupling. So, and now on the other side, there are essentially the two similar strategies, but acting on different parts of the system. First, you can say, okay, I can decrease the charge noise and keep the same coupling strength. And in fact, this is what Jason did. So he found a system which is based on silicon, which is much more silent, and therefore you can decrease very strongly the gamma S. And if you still keep a gamma G perpendicular to about the same values, around 10 to 100 megahertz, you will reach the strong coupling regime. In our case, it's also about reducing strongly the gamma S, but essentially the idea is as follows, is that in all these cases, we would like to be closer to a sweet spot of the transition as a function of the control parameters. So for example, a sweet spot, so if I go back, so you see here, for example, you have a minimum in the transition frequency as a function of the detuning, and this is primarily the detuning which is mostly sensitive to the charge noise. So if you see it here, you will be insensitive to charge noise at first order and only sensitive at second order. And at second order, essentially, this is the second order derivative. But what is important is that what the energy scale which enters this sensitivity is the power spectral density of charge noise times the charging energy squared, because this is how you translate a charge number to an energy scale. And now if you decrease the charging energy in a similar setup, you will decrease very strongly with a quadratic decrease the gamma S. And in our case, we decrease the charging energy with respect to similar setups before by a factor of 10, which means that it would decrease by a factor of 100 overall the gamma S. And if you remember that we had 500 megahertz for the previous work that I showed you in a similar setup, this means that we can reduce to about several megahertz this line width and reach again the strong coupling regime. Okay. So as a conclusion of the first part, I have shown you that it is indeed possible to achieve the strong coupling regime between quantum dot circuits and microwave cavity photons. So this could be used, I mean, this kind of methods, all the methods, in fact, we could imagine to combine all these methods which have allowed different groups to reach the strong coupling regime, to get the spin photon coupling. This is one thing which we talked about yesterday, and so along the lines, for example, let's say the immediate perspectives of this work is for the charge degree of freedom to do an ultra long distance coupling of double quantum dots, because now if you have two double quantum dots sitting in two different pockets of the resonator, and we saw in the lecture that these are macroscopic distances, about 10 millimeters, we could imagine to couple these microscopic charge degrees of freedom over macroscopic distances along, for example, the lines of this proposal by Guido Burkhardt and attached Malloy. Okay. So this is for the first part. But now the question is, this is more atomic physics-like, so we have an atomic-like system. It's a few level system, and we would like to use it to engineer it in order to achieve the strong coupling, to do quantum manipulations for quantum information processing. But I'm going to show you now in two examples that we can use this kind of architecture for addressing more condensed matter questions. So we started already yesterday, so we looked at this system. And but in this system, you have interactions, but you don't have correlation effects really. Because you have a strong Coulomb blockade with weak tunneling. So we would like to go to another regime where we have strong tunneling and Coulomb blockade effects, and this allows us to investigate a very important problem in condensed matter. And so maybe this is maybe my favorite problem of strongly correlated systems in condensed matter is Kondo physics. So this is Kondo physics in alloys. So this is the increase, for example, if you take an alloy of like copper iron and with 0.2% of iron in it, below the Kondo temperature, you have an increase of the resistivity, and which was there was a starting of which was understood somehow by Kondo in the 60s. Although these measurements, these kind of measurements were done as early as the 1930s. And let's say the modern way of understanding that kind of system is, in fact, resembles very much what we are able to do in the lab. It's the fact that you can model, this is the Anderson model of a magnetic impurity. You can model a magnetic impurity by telling that you have a site here with an unpaired spin, which is separated by the charging energy, so for double occupation. And there are fermionic continua here, which are strongly coupled to this impurity, and this can be mapped, in fact, onto a spin problem using the Schrieffer-Wolff transformation, which we heard about this week. And in fact, this is the simplest many-body problem one can think of, because you have just one energy level, plus Coulomb repulsion, plus a Fermi C. But it's actually relevant to many condensed matter systems. It's like a test bench of many theories, and also in many situations in strongly correlated matter, you kind of go back to a Kondo problem. So this is why it's so important, I think. And essentially, the way to understand why, for example, there is an increase of the resistivity at low temperature is that, in fact, you form a bound state for the electron spins, which lead to a peak in the density of states at the Fermi energy of the host, like here is going to be the leads. And in fact, in transport in quantum dots, this has the consequence that you're measuring a peak where you would expect nothing. You're measuring a peak in a conductance, and this can be studied with exquisite details as a function of many tuning parameters, the magnetic field, the gates, in many different situations by conventional transport techniques. In fact, there is one thing which you cannot probe directly when you're doing transport, is in fact the way this resonance builds. So this is a cartoon picture of how it works. So in fact, if you consider the situation where you have a spin, an unpaired spin on the energy level, and you have an opposite spin on one of the reservoirs. So there are two kinds of virtual processes which can occur. So the first one is that you can empty the dot. Of course, this is not allowed by conservation of energy, but it's allowed quantum mechanically for a small amount of time. And so this is this kind of virtual process. So this spin goes here, and this spin here fills back with the opposite spin, the dot. So there is the symmetric process where essentially you fill now this this dot with the second spin, which is opposite, because it has to be opposite to be able to fill the same state. And you empty this dot with the opposite spin. And from here to there, you have flipped the spin, but you have not changed the charge. So the charge is the same. So the charge is essentially frozen. And this decoupling of the spin and charge degrees of freedom, because the spin fluctuates all the time and the charge is frozen, is absolutely is not usual, of course, for a resonant level. And this is one important. I mean, this is maybe like one very important aspect of the Kondo system, which in fact we will observe directly here. And what is interesting here is that you see that this kind of processes will also contribute to current, because now I have to transfer the charge from the left to the right, although the charge sitting on the dot is completely frozen. And so is it possible to observe that you can have a conductance, from the frozen charge on the dot, this in fact is not possible to observe that with conventional transfer techniques, but I'm going to show you that with the cavity you can indeed observe this directly. So here's the setup. So again, it very much looks like the setup for the double quantum dot. So you have essentially the cavity here, and now you have the nanotube, which is a single dot nanotube. So you have a bottom gate, and this bottom gate, in fact, is capacitively coupled to this fork here, which goes to the central conductor of the cavity. And on the other side, you have a DC gate, which is also capacitively coupled to this bottom gate. So this bottom gate is made primarily to favor the fact that the photons will shake only the gate, only the epsilon d, and not the leads here. So for the device, I will describe in the next view graphs. This is in fact what is happening. Although it's not fully, I mean, sometimes it's not as simple as that. Okay, and so in this setup, we simultaneously measure the conductance and the microwave response, so that the transmission here and the conductance flowing through the device, which means that since we have seen yesterday that the microwave response is a direct proof of the compressibility of the system, we can measure directly in a way the conductivity and the compressibility, which in strongly correlated systems, in fact, are different, I mean, quantities and are differently, I mean, are sensitive in a different manner to correlations. Okay, so the first thing which we can do is to check that, to calibrate the coupling between the electron and the photons. And for that, we take a very well-known situation, which is the Coulomb blockade regime. And so it's a bit similar to what we saw yesterday. Essentially, I know the chi, I should expect it will be roughly like this 2 pi over times 1 over gamma, which we wrote down on Blackboard yesterday. And on each charge peak, so you see here the conductance you have as a function of the gate electrode, you have charge peaks here. So on each charge peak, I would expect to have a perfect correlation with the microwave signal and to have peaks in the compressibility. And as I told you, the phase contrast in that kind of situation is negative. So minus the phase is just the compressibility, as we saw yesterday. And you see, if I plot minus the phase, I have positive contrast of about several degrees, which is, so I have peaks which are perfectly correlated with the charge peaks. So this is close to equilibrium. So in what we call the linear regime, so in the sense that the bias now which we apply to the quantum dot is zero. And we have a small oscillating but very low frequency bias to measure the conductance. And this is what happens in the nonlinear regime. So when we now apply finite bias, that's the Coulomb valley here. So there is, in the Coulomb valley, we see no signal in the conductance and no signal in the phase, in the cavity. But then when we reach a Coulomb peak here, we see a perfect correlation between, the conductance signal and the cavity signal. And this is somewhat expected because, I mean, this is exactly a situation which we sketched in the blackboard yesterday. That, in fact, in this situation, we are in this regime, so which is called the off regime, where essentially the charge is not able to fluctuate, and therefore, in this case, since we have no correlations, essentially we have zero, I mean, conductance and zero compressibility. Whereas on each charge peak now, we align the energy level to the Fermi energies of the reservoirs, and therefore the charge is able to fluctuate, which leads to these peaks, both in the conductance and in the compressibility. So this allows us to, from the phase contrast, this allows us to calibrate the coupling strength, and we find values, I mean, of about 100 megahertz, which are somehow, which is on the high side of the expected values which we would have, and this validates, let's say, this bottom gate geometry. So we can further characterize let's say the sensitivity of our system about, I mean, so if you look at the noise here in the phase, this would correspond to a charge sensitivity of about 210 to the minus 4 electrons. And in fact, this compressibility contrast here, if you plug in numbers, is around 100 per electron volt. And this is somehow 7 orders of magnitude smaller than what you would expect from a piece of metal of 1 micron cube, which would be 10 to the 10 per electron volt. And this is somehow expected because you have a much smaller density of states. But this shows you the sensitivity of this architecture for measuring tiny compressibilities. Okay, so now, we have, I have shown you that we have coupled electronic and photonic systems. Sorry.
The compressibility curve is slightly broader than the conductance curve. It doesn't go to zero as hard in the middle of the valley. Do you understand what that is?
Quantitatively, we don't understand, but we think that this is because actually these are cotunneling processes which we see better in the compressibility than in the conductance. But we don't have a quantitative understanding of that. We think that's yeah, you're right. So this might be so okay. There are some also other effects which you see that also it's not for some peaks it's not perfectly aligned. So we think that this might be the start of the onset of correlation effects because you renormalize by virtual tunneling processes the energy level. So this might be something related to that also, the fact that it's like there is slightly more. I mean, it's like slightly more compressibility than the conductance. In fact, we see in the Kondo regime things even much larger effects as you will see. But you're right. That's absolutely correct. So and now the question is we have two well-coupled electronic and photonic systems. What about in the Kondo regime? And for understanding what's going on in the Kondo regime, I just have to turn the knob of my. We don't do that. I mean, in the lab. I mean, These are, of course, interfaced DC sources, but let's say we turn the knob like this. So we turn the knob to crank up the gate voltage, and by doing this, we will increase the gammas between the electronic level and the reservoirs, and we will see hopefully Kondo physics. And in fact, this is what you see here. Is that the diamonds are become completely blurred. So here, these were the Coulomb diamonds, which is in the Coulomb blockade regime. So pretty well-defined diamonds. And of course, since you increase the gammas, the diamonds get blurred. But what is important is that now you see that you have horizontal lines here. And these horizontal lines, if you do a cut, these correspond to zero bias peak. This is the conductance in blue. So this zero bias peak is the hallmark, I mean, of this of the Kondo peak, and it's exactly this many-body resonance which I was telling you about. I mean, at the beginning of this part. But what you see now is that, so you see also that you have big bumps here, and these big bumps are the charge bumps here. So at this, there and there, the charge is able to fluctuate, but here we don't know what is going on. And in fact, the cavity tells us what is going on. Here you see that the phase now, it's of course sensitive to the bumps, although it's not perfectly correlated, but it's completely insensitive to the presence of the zero bias peak. In other words, the Kondo resonance is completely transferred to the photons while the charge peaks are visible. And this means that this Kondo peak is incompressible, and that this measurement, in fact, is the observation of the freezing of the charge degree of freedom in the Kondo system. Because you see that you have a peak in the conductance, so you have charges which are flowing through the system, but just through these virtual processes which I have sketched you before, which involve spin fluctuations. And this is a direct demonstration of that, because the cavity has absolutely no signal. So we came to our colleagues, Minchuli and Mansu Choi, who did the numerical renormalization group to understand both the equilibrium. So this is the compressibility is the equilibrium quantity, right? So they can calculate this with energy, and they can calculate also the spectral density, which is what we measure with the conductance. And you see that this is they qualitatively reproduce what we observe. So you have in blue a peak. This is the Kondo peak, surrounded by bumps, charge bumps. So these are high energy charge fluctuations. High energy means on the charging, the Coulomb energy on the charging energy. And what you see is that there is absolutely no compressibility associated to this Kondo peak. And whereas there is, of course, compressibility associated to the charge bumps. And there is also a shift here. You see this shift. So, of course, here there are some complexities of the samples. This one we have a qualitative agreement only. But what is important is that you see there is a shift here between the Kondo, the bump seen in the Kondo, in the conductance, and the bump seen in compressibility. So we think that this is a correlation effect, which has to do with the renormalization of the energies on the energy levels from virtual tunneling processes back and forth to the reservoirs. But what this measurement shows is that really it shows the fundamental difference between the Kondo resonance, which is a many-body resonance, and the resonant tunneling, for which you would have both a peak in the compressibility and in the conductance. So, of course, we can do this. We can study this on many Kondo peaks, because in our device we have many shells where we had Kondo peaks, and in fact you see that all the time that there is a peak and nothing in the charge compressibility here, for example, here. So this is very reproducible effect. So for the fact that each time you have a Kondo peak, it corresponds to an incompressible state. There is absolutely, it corresponds to a frozen charge, essentially, And so I think this is the first observation of the frozen charge of a corner resonance. Okay, we can look at the temperature dependence. Yeah. So in fact, so you see, this is exactly what we saw yesterday. So on very basic grounds from linear response theory in the adiabatic regime, you can say, okay, my cavity is measuring the compressibility of the system. Then you're free to choose any kind of technique which you like in the adiabatic regime to calculate the compressibility of the system. And what Min-Soo Lee and Man-Soo Choi did is to calculate the compressibility with the numerical renormalization group. Then, of course, this is only, I think it's, okay, it's for the Kondo problem, yeah, there is not, but then, of course, there is no full theory when now, if the Kondo temperature was comparable to the cavity frequency, of course, this would not apply. And then we could not write down the simple formula like this. So this is, here the Kondo temperature was about 250 gigahertz, so it's okay. You know, we're really in a adiabatic regime. But if now the Kondo temperature would go down, then it would be a different story. Yeah, but in fact it's a Fermi liquid, but okay, but it's a special Fermi liquid. You see, in fact, of course, the low energy physics you can recover a Fermi liquid, but it's built in from this freezing of charge dynamics. Yeah, that's true. But this shows the fundamental. So this shows you that indeed, what we were thinking at the beginning is that, well, okay, we will see the Kondo peak in the cavity. This is a low energy argument, because essentially the density of states, since you have a Fermi liquid, should be essentially the same as to give you the same piece of information for both the conductivity and the compressibility. Yeah, exactly. Exactly. But this is what this measurement shows you directly. So that the spectral density which you measure is something which is not related to the charge. It's related to another degree of freedom, and in our case, it can only be the spin and or the valley. Yeah. Well, I don't. So the compressibility is just the derivative of the number of particles when you change the derivative of the number of particles with respect to the chemical potential. So this is a direct measurement of the compressibility. I don't have to do any further assumption. It's the compressibility of the system which is measured. But then you're right. This is surprising. Although this is a Fermi liquid at low energy, this is still an incompressible charge state. That's exactly what is measured. It's measured in this experiment. Okay, and then we can study the temperature dependence. And the temperature dependence, you show some scaling in the conductance. So we have a different, let's say, parallel in the phase. But the parallels are maybe not so important. What are important is that you see the downturns. So you have some kind of saturation of the conductance at low temperature, and then it starts to go down. You have also saturation of the phase contrast of the compressibility at low temperature, and it starts to go down. But the downturn here occur at different temperatures. So this is in log scale here. And this is very well reproduced by the qualitatively by the energy. And this is this measurement shows that the conductance and the phase or the compressibility are evolved on the temperature scale, which is corresponds to different energy scales. So the conductance evolves on TK on the energy scale, which is related to TK, whereas the compressibility is just related to gamma. And this is what is shown here. Okay. So so what can we do next? Now we have a strongly correlated system, so coupled to a photonic field, and we could imagine also to use this for some kind of quantum simulation of strongly correlated electronic systems, because now we can do a mapping between the photonic field, which we measure directly, to the photons, and in fact you see that this is the Hamiltonian which we wrote together, and this is Holstein-Hubbard Hamiltonian, which is the one which is, for example, heavily used in a strongly correlated system. For example, in this paper, this was for high-density superconductors, where essentially you have the similar density boson coupling. Here there are several modes. You have the charging, the on-site charging, Coulomb repulsion. And in fact, this kind of, the fact that the bosonic mode are not sensitive to the low energy part of the physics, so the low energy part for them, as I explained you, is a Kondo type correlations. It's in fact, I mean, something which was already, let's say, found in these kind of models, that the bosons decouple to the high energy part of the spectral density. So the high energy part means the charge bumps for us, but not to the low energy part, which is Kondo-like. And that's exactly what we observed in this experiment. So this is why we maybe want to go further and study this, and use this maybe as a quantum simulator for fermion boson problems. Okay, so that's the conclusion of part 2. But as I told you, so we have 15 minutes, like 13 minutes. So we can do more. But let me summarize what we saw in this second part. So it's more a condensed matter perspective, so that the cavity can be used as a very sensitive probe of strong correlations. And this has led us to the observation of the frozen charge of a Kondo resonance. So the perspective of this setup are what I showed you yesterday. So for example, the probe of quantum transport in mesoscopic circuits generally. But also we could imagine to do some kind of quantum quench of the Kondo cloud by shining a large power in the cavity, or generally quantum simulation of fermion boson systems. But we can also imagine to go further and to probe even more exotic states in condensed matter. And the exotic states, as you anticipated already, is the Majorana states. So it's exactly the same reasoning as before, but now we will use a slightly the full, I mean, expression which was established in this paper, but applied to a different context. And why we want to do that is because this is exactly what Jason said yesterday, is we want to go beyond transport measurements and beyond the zero bias peak. So essentially the idea is that these Majorana excitations should live at zero energy, essentially, and are self-adjoint, they're their own antiparticle, and they could be used, of course, to do some maybe interesting, ultimately, topologically protected quantum computation. But what is very important is that since they're living at zero energy, the first idea which was used in all these papers, and there are many other people continuing to do this, is essentially to say, okay, I will do talent spectroscopy in the system, and if I see a zero bias peak, this will be the signature of Majorana fermions. This was already done in this very influential paper by the group of Delft, and also more recently by the group of Copenhagen, with even higher quality of data and more, I mean, pronounced effects. But the problem with this kind of measurement is that you see that you have a zero bias peak here in the conductance, well, of course, it's not perfect. You see, there is always some imperfections in the experiment, as usual. But on a more fundamental way is that besides the imperfections that you could imagine, and there are many theory papers and also experiments which show you that this kind of zero bias peak is not a unique signature of Majorana fermions. So you could have I don't like the wording trivial, but okay, what people call trivial zero energy and real states. You could have also competition between Kondo effect and superconducting correlations. You can have weak anti-localization. In fact, each time there is a new experiment appearing, there is a new theory paper telling, no, but this is not Majorana fermions. It's something more complicated. You have energy levels. You do not observe this. And then when they observe this, they say, oh, no, but this is, again, even more. I mean, you should do even more to be completely sure that this is really Majorana fermion. So we also would like to observe this in different contexts, but we would like to go beyond that. And how to go beyond that? You know now that I am a bit stubborn in this. So I would like to use cavities to go beyond that. And so let's see. So the cavities are interesting for a reason which will become clear in the next few graphs. And it's related to the fact that the Majoranas are their own antiparticles, so the operators are self-adjoint. And this, in fact, completely puts a very strong constraint on the coupling between these Majoranas and the light. And in fact, you have a very simple Bloch sphere, essentially representation of that, which I like particularly. Imagine you have a pair of Majoranas. So the only, let's say, Hamiltonian, non-trivial, which you can make out of that is just I epsilon gamma 1 gamma 2. And why is that? It's because they are self-adjoint operators. So, which means that if now you look at the coupling between these Majoranas and the microwave field, the only thing you can have is exactly the same with a different proportionality constant. But this means that in the Bloch sphere language, so this guy now is commutes with this guy, it's proportional. In the Bloch sphere language, this means that this is the DC part of some kind of effective magnetic field, although it's not fully equivalent, this pair of Majoranas to spin 1/2. But let's say that there is some kind of effective Bloch sphere. This is the unperturbed term, and the photons are shaking along this unperturbed term the energy of the system. So this means that we have a longitudinal coupling, and it's a purely longitudinal coupling. So this longitudinal coupling means that essentially the pair of Majorana, although it interacts, will never shift the cavity of frequency, because essentially these two guys commute. So and so in fact, so now we will apply this idea to show that we can have a setup where we will make use of this selection rule related to the Majorana excitation. So what Mathieu, Dartier, Audrey, Cotet, and Benoît Dussault did is that they took the Kitaev chain, so the spinful Kitaev chain, and they used this formula for the charge susceptibility. Now, there is the energy, the frequency dependence. And the structure of the G's here now includes the site of the Kitaev chain, the spin, and the number for the electron-hole symmetry. And essentially, with this kind of setup, you can put eternal electrodes, so you can calculate the spectral density. And what you see is that as a function of the external magnetic field, you will have essentially what has been observed, for example, by Albrecht. So there is precursors of Majoranas, and they're merging at zero energy. And there, I mean, these Majoranas are well-defined particle and antiparticle excitations. So, but of course, there are some other energy scales and other energy levels which are related to excited states higher. And now, the idea is to now see what's going on with the cavity response. And this is what is going on. In fact, this transition is completely forbidden. And why it is forbidden is because exactly what I told you. This is a pair of Majoranas, and this internal transition is forbidden due to the self-adjoint property. However, even though you have a tiny continuum, and this can happen, for example, if you have a residual density of states in a superconductor, so the cavity will be able to probe very sensitively processes where you essentially add a quasi-particle to one of the two doublets of this Majorana precursor. So here. So if you look at the transport, what you will see is that you will see essentially precursors of Majoranas with a splitting which will be 2 epsilon, symmetric with respect to the Fermi energy. And you will see nothing at this energy. This is process A. So this is forbidden due to self-adjoint property. But you will see a step which is photon-assisted tunneling processes between one side, I mean, one doublet, one partner of the doublet, and the continuum. And this will tell you that, okay, this self-adjoint, this transition is forbidden, but nevertheless, the Majoranas are coupled, but only in a longitudinal manner to the cavity photons. And this will allow to probe directly the self-adjoint property of Majorana quasi-particles. And I think I'm done now. So I would like to thank you for your attention.
You had a formula, you got something for this B out by B in terms of compressibility, right?
Yes, exactly.
So now what you're saying is that that formula holds whether you are in the Kondo regime or not.
Yes, exactly.
The only thing that changes is the computation of compressibility itself.
Exactly, exactly. But so in the adiabatic regime.
So I'm confused.
So when the cavity is much lower than the relaxation probe, but then the dynamics of the.
I see. So the adiabatic regime and Kondo regime are consistent. They can go together. I mean,
yes, exactly. Absolutely.
Okay.
Yeah, absolutely.
When you say adiabatic regime means that the compressibility is a static probe?
Absolutely, yeah. It's a thermodynamic property, yeah.
Okay.
So just a follow-up. So of course you're probably planning to try something beyond a diabatic regime, right? Because then you can get much more richer physics.
Absolutely, absolutely.
So is this something you're?
Yeah. So the idea is to now. So now the Kondo resonance was too large. I mean, it was not in the microwave. I mean, it was in the microwave range, but like in a high microwave range, let's say, or in a sub-terahertz range. Now we have observed in this kind of devices, Kondo resonance is below 20 gigahertz. In this case, we would expect to see very strong non-adiabatic effects.
Hi. So can you please explain why Majorana does not couple to the photons? That's what you were trying to say.
So it couples to the photons, but it couples only longitudinally.
Yeah. So why not?
So it's here. So you see, so that if I have a pair of Majoranas, I have two self-adjoint operators.
You are considering they overlap.
Even when they overlap. But even when they overlap. Okay. If they don't overlap, I mean, this thing is zero, this thing will be zero. If they don't, and so everything is zero, you just have the cavity. But the point is that when...
It's not supposed to overlap. Right?
Absolutely, absolutely. So the question is how to probe the precursor of the Majoranas before they vanish, essentially.
So you will not detect the true Majorana, but you will see some kind of andrift or some kind of low-lying andrift states?
So in fact, it's, well, okay, there is some semantics or some wording. I mean, so I will see, let's say, if you will, andrift states which are non-degenerate and which are therefore precursors of Majoranas by continuity. So if I see, you see here that these precursors here have you know, it go to zero here. This means that when I extend the system here by continuity, these are Majoranas. But of course, I mean, if they drop out the Hamiltonian, it's going to be difficult.
I don't understand how will you then detect the true Majorana through all this kind of experiment.
But there are not true Majoranas and false Majoranas, right? They are essentially particles which are, I mean, their own antiparticle and which can overlap or not overlap. There is no sense of true Majoranas and false Majoranas. You understand?
I think what he means is probably in the regime where you have actually Majorana bound states is what he's probably.
No, I mean that when nano is long enough that Majorana does not overlap.
Yeah, in this case, it's impossible to detect them. Yeah. But these are not true Majoranas. They're let's say these are Majoranas which don't overlap, which is different.
So just a follow-up question. All your work you've done so far has been on carbon nanotubes. And for Majorana, you want strong spin orbits. Are you going to switch materials, or you have other plans to have strong spin orbit plus proximity effects?
Well, in fact, yes. So we have a work where we have engineered a synthetic spin orbit interaction in nanotubes. So we have plans to stay with nanotubes because they are more one-dimensional systems. Well, so this is why we think that the nanotube platform is still very interesting because it's more one-dimensional and we don't have the hard gap problems. So we want, if there is also generalized to many out of the platform. So, for example, if we get nanowires with this epitaxial aluminum, the Charles nanowire. So then we'll be happy to measure that, of course.
So just to kind of understand his question, so what exactly is this system you're using here for getting Majoranas?
So well, here I have not shown. So the idea is to build to continue with nanotubes, not just because I like nanotubes, but also for that. But it's also because they are, I think they are more one-dimensional systems, so they have much less channels, for example, and the number of channels is an issue also in nanowires. So continuing with nanotubes is interesting, but then you need to find a means to engineer a very large spin-orbit interaction. And so we do this by having a magnetic texture.
Sorry, a magnetic?
Texture, which is coupled.
That's how you, this explains.
That's how we will do, yeah. That's how we will do it.
Other questions? So I actually had a question in the first part where you had a superconductor that you had on top of a nanotube. So in that case, the nanotube doesn't, I mean, are there any kind of effects, proximity related effects or things that, I mean, are you totally ignoring all those kinds of things?
No, so there is proximity effect, but in a very, let's say, in the atomic limit. So the presence of the superconductor renormalizes the spectrum of a double dot, and you have the so-called elastic co-tunneling process. So we have quasi-particles which essentially tunnel through the gap of the, or essentially you have a virtual process which when you create essentially virtually a Cooper pair in the superconductor with a quasi-particle, and then you have a quasi-particle which goes back on the other dot. And this is related to the superconducting correlation. This is what some people call elastic tunneling in the physics of non-local superconductivity.
Okay. So if there are no other questions, let's thank him for his last lecture.